We've gone over the stresses in the concrete and the stresses or the stress in the steel rebar. Let's now think about the amount of steel. There must be some kind of limit. There must be an upper limit and a lower limit to the amount of steel. So let's talk about that first. Before we do that, let's just talk about too much and too little. Uh, what the effects are. So time. So if you have too little time, you're rushed. If you have too much time, you could procrastinate. Sugar. Too little sugar, not sweet. Too much sugar, oversweet. Water. Too little, dehydrated. You could die. Too much water. I forget what it's called. It's called hypotrapnia, hypotonia. Uh, but you can die, and especially in a marathon. If you drink too much water without electrolytes, what happens is it flushes out all the electrolytes in your body, and you feel really bad. Too little sleep, you're tired. Have you ever taken a nap too long or slept too long? You woke up and you're all tired because you slept too much. So these two here is kind of weird. Um, Too much and too little have the same effect. And it's a similar thing with steel in an RC beam. Too little, and instead of being ductile, the beam is brittle, and too much, the beam is also brittle. How can that be? Too little and too much steel both make the reinforced concrete beam brittle, not ductile. So let's first talk about too much. There's a little bit of history about the maximum amount of steel you can put in a reinforced concrete beam. And what I'm going to do is I'm going to trace the development of this and discuss the behavior. So we're going to start off, even though this is in the code anymore, we're going to start off with something called row balanced, the balanced amount of steel. Okay. So a balanced beam. And what I mean by a balanced beam is that the steel will yield simultaneous with the concrete crushing. Okay. So we've already talked about this several times. We're assuming the strain at failure in concrete is 003, and the yield strain of the steel is just the yield stress, Fy, divided by E. Okay. You get this strain diagram by similar triangles. You could find C, and we're going to use our equivalent rectangular Whitney stress block. We can get that stress. We know that the steel is yielded by definition. We just said it's yielded. We could get that. And what we're going to do is solve for the amount of steel that makes this happen. So from this strain diagram, okay, so let me just redraw that here. Okay, that's 003. That's C. This is Fy over ES. The overall height is D. So D is the distance from the top of the beam to the center of the steel, which makes this distance here D minus C. So by similar triangles, C is the 003 as Fy. Oh, we're going to do this triangle. Sorry. Let me redraw it. We'll do this triangle here, this big outside triangle. That's D. And the total distance here is Fy over Es plus 0.003. Okay. So what we're going to do is say C is to 0.03 as D is to this, Fy over Es plus 0.003. Okay, so there. So there's the two similar triangles. The yellow triangle is similar to this green triangle. And here's the yellow triangle. Okay. Solve for C. Okay. You get this. And we know the neutral axis is now there. Equilibrium, T equals C. Okay. So this rectangular block, the stress is 0.85 F prime C. This height is beta 1 C. Okay. And then there's a width to the beam of B. Okay, the stress of the steel is Fy, and there's amount of steel. It's the special balanced amount of steel. Solve for AS balance, and believe me, it comes out to there. Okay. We want to do everything in ratios. So we're going to take rho balanced as the ratio between this balanced amount of steel to the area of concrete B times D. Now, here's the steel. This is H. D is the distance to the steel. So we're taking this area of concrete, the area of concrete down to the steel. Okay, so divide both sides of this equation by BD, and then it's nice. The BD cancels out, and you get this. Okay. Multiply everything by ES to get this ugly thing out of the denominator. So multiply numerator and denominator by ES, and you get this. So you get rho balanced. Okay, so rho balanced equals 0.85 beta F prime C over Fy 87 over 87 plus Fy. Okay, so that amount of steel will make the steel yield exactly when the concrete crushes. Okay, so next is rho max. Okay, we have the balanced amount, and now we have rho max. Okay, so we want to make sure that the steel yields. Can you see it makes sense to have less than the balanced amount? Because you make the steel weaker, so the steel will fail first. And so think of this like a chain. So when you pull on a chain, it's going to break at the weakest link. And you can think of a concrete beam as having two links, compression and tension. And you want the tension to break before the concrete. You want to make the steel the weakest link, because when steel breaks, it stretches and deforms. But when concrete breaks, it just explodes. So what you want to do to guarantee that the steel is the weakest link, we're going to take only 75% of that balanced amount, and that's going to be the maximum amount of steel. This will guarantee, okay, it'll guarantee that the steel fails before the concrete. This was in the code before 2002. Okay, so from 2002 to 2014, another way to ensure ductile behavior is to make sure the steel strain is large. And so if you make the steel strain greater than 0.005, this guarantees that it'll be ductile. And what we're saying is, here's 0.003, and this is epsilon steel. Remember, we want it bigger than epsilon yield by quite a bit, because if it's bigger, that means it's yielded. And so epsilon yield, let's say for 60 KSI, if you take 60 divided by 29,000, that comes out to 0.00207. And so this, if the strain there is 0.005, it's significantly bigger than 0.00207. It's definitely ductile. And what we're going to do is use a strength reduction factor of 0.9. We talked about that in the beginning lectures. You calculate your moment strength, but the reliable moment strength is phi mn. You're going to reduce it. And so if it's something ductile controlled by steel, you reduce 10%. And then for 0.005 to 0.004, you would use a lower phi. And below that, you're not allowed to do that. Then it would become basically a column controlled by compression. Okay, so just in 2014, this changed again. So this magic number here, 0.005, was calibrated to Fy equals 60. I've checked it. The amounts of steel from here, the maximum amount of steel from there, matches the maximum amount of steel from here for Fy equals 60. Well, what if you have a yield strength that's not 60 KSI? What they've done is that 0.005 magic strain number, they've replaced it with 0.003 plus the yield strain. And remember, I just said this was 0.0207. Just round that down to 0.02, and that comes back up to this magic number. This way, if you have a different yield stress, you can fix it. And this number comes out to something smaller than 0.005 if Fy is less than 60. And if, okay, so if your steel is less than the yield, it's definitely failing in compression first, so you're going to use 0.75. And if steel is greater than this number here, which remember is basically 0.005, then you use a 0.9, and in between you'd interpolate. I wouldn't do this. What I would do is just make sure your epsilon steel is greater than just make sure the strain in your steel is greater than 0.005 for grade 60. And here's how you calculate the yield strain. Okay. So next, on the next video, we're going to talk about the minimum amount of steel. So this is the maximum amount. Okay? Make sure the strain in the steel is at least 0.05. The next video is going to talk about the minimum amount of steel.